Now, time to move on to level 2 on complex impedances. Right, first question. Okay, it's a build a circuit question. We want to make the impedance 733 ohms at minus 81 degrees using two components. Well, things like this, again, it's helpful to think about the Argand diagram representation of complex numbers. Now the total impedance here we want is 733.3 at minus 81, so it's going to be right down here at minus 81 degrees, so that's 81 degrees clockwise, and 733, so that's the length of this line, 733.3 ohms. Now, in order to make that, we have a resistor here of 120 ohms. So supposing this was the series combination of a resistor that's 120 ohms, would that actually work? We can easily work that out by just looking at the distance here. And we can work that out using the cosine of the 81 degrees here. This right angled triangle here, we have 81 degrees, we know the hypotenuse, 733.3 ohms, so we should be able to work out that distance there. It would be just 733.3 times cosine of 81 degrees. And with a bit of help from a calculator, $114. Well, that is probably within the accuracy of the calculations to 120 ohms, or 120 R. In other words, what we've got here is 120 R here, 120 ohms, plus this impedance down here. And that, since it is going in a negative imaginary direction, must be a capacitor. Inductors go up, capacitors go down, so that must be 1 over j omega c. At this point here, I could note that I've only got one capacitor that it could be, therefore it must be 120 ohms in series with that capacitor. But if I wasn't sure about that, then I could work out the capacitance here. 1 over j omega c here, or at least the magnitude of it, is the length of this side of the triangle, which I could calculate from 733.3 times sine 81 degrees. So that's going to be approximately 724 ohms. And that is 1 over omega c, therefore c would be 1 over 2 pi times the frequency. The frequency, I'll just check, 10 hertz. 10 hertz times the 724, which is 2 times pi times 10 times 724, take the inverse of that, answer 22 microfarads. So if there was a 22 microfarad capacitor, then putting that in series with the 120 ohm resistor should give you 733.3 at minus 81 degrees. And indeed, we have got a 22 microfarad capacitor. So, just wire it up, and we're done. As I say, we could have done that much quicker by just noting that whatever was going to be in series with the 120 ohms had to be a capacitor, and therefore this is the only option. And I note that this has to be a series combination, not a parallel combination, because the total impedance here, 733.3, is bigger than 120, so I must be adding something in series with the 120, not in parallel with it. And it can't be a capacitor and an inductor, because if it were, the angle would either be plus 90 or minus 90, couldn't be anything else. Right, try another one. This is easier, actually. This is just a parallel combination, so the answer is 1 over the impedance of this arm, 3K9 rather, plus 1 over the impedance of this arm. And that is j omega L, in other words, j times omega, 2 times pi times 5K. That's my omega, because the frequency is 5 kilohertz, times the inductance, which I can just add up in my head. That would be 1.33 henries. 1 henry plus 0.33 henries. Right, done. Not so bad. Next one. Another one fairly similar. I've got 180 plus the parallel combination of these two. So that's 1 over the impedance of a capacitor, which is 1 over j times 2 times pi times 100. Again, that's our omega, times 6 mu 8, plus 1 over the impedance of the inductor, which would be j times 2 times pi times 100 times 0.33. And just be a little careful to get my brackets right. There. Fine. If you're a little uncertain about getting all the brackets, then you could always have worked out the impedance of the capacitor down here and the impedance of the inductor down here and just used x and y, and in hindsight that would have been a good idea. Next one. Work out the missing value of this inductor. Well, if the total impedance is 2.86 meg at 46 degrees, and that is going to be the sum of the impedance of these two resistors and that inductor, then the impedance of the inductor must be the total minus 470k minus 1 meg 5. In other words, that. Rather reassuringly, this is at plus 90 degrees, which is what you would expect the impedance of an inductor to be, because it's j omega L. That, then, must be omega L. So if I take that and divide it by omega, I must be left with L. Fine. Next. Okay, perhaps a slightly more interesting one. This time, given a total impedance, the circuit is a bit more challenging to solve, but the same type of idea works. The total impedance is 1.15k at 4 degrees. And 1 over that total impedance is going to be equal to 1 over 1k6 plus 1 over the total of the impedance up here. So if I take that total and subtract 1 over 1k6, okay, so we've got 0.00025 at minus 14 degrees, and that is 1 over the total impedance of these two components here. So if I take 1 over x, that should give me the 15 millihenry impedance plus this unknown resistor. And if I subtract, therefore, the impedance of a 15 millihenry inductor, which is j times omega, which is 2 pi times, in this case, 10 kilohertz, times the value of the inductor, which is 15 milli, I should be left with just the value of that resistor. And I get, yep, it's real. 38891, and it's real, which is reassuring because as a resistor it should have a real impedance. That would be my answer then. Oops. Y. 3K8. And yep, there's a few rounding problems, but it's close enough to be correct. I could probably have guessed that the answer was 3K9. It's the nearest E24 value. I'll just do one more.